Okay, so let's finish out vectors day 2. So looking right here at our 7th example, we have some steps that you can work with multiple vectors. You have to find our component form of each vector. We're going to add those in order to get the resultant. And then we'll find the magnitude and direction of that resultant vector. Now, one thing I want to mention, when we get kind of deeper into these, you're going to have a lot of times talking about what's called ground speed, which is like your actual speed, air speed, and wind speed. So I'll write this little equation real quick. G equals A plus W. Okay, if you want to put those as vectors, that's totally good with me. So I'm going to come back to that equation here in a little bit. But here's what's happening. Just like we did on day 1, adding vectors, we're going to do the same thing here. So if you have two vectors, right here we have U and V. So if I was to write the component form for vector U, remember it's magnitude times cosine of our directional angle and magnitude times sine of our directional angle. So we have 6 cosine of 20 and then 6 sine of 20. Okay, if we want to, we could type that in our calculators to get the decimal equivalencies for that vector U. I'm going to leave it like this for the time being. And now let's do the same thing for V. So vector V would be our magnitude, which is 3, times cosine of 150, and then 3 times sine of 150 degrees. Okay, so we have our two vectors in component form. Now, what we're going to do is, we're going to take U and V, and we're going to add them together. Okay, so on our day 1, it was just simple numbers that we can add. So now we're going to be actually adding our magnitude and directional angles with these cosines and sines all together. This is where you would use a calculator. Make sure your calculator is in degree mode. So you can see if I had U plus V, I would take these two and add them together for the horizontal component form, or component of our vector. And then we would take our vertical components and add those together in order to get our U plus V vector. So if you do that, I'm going to go and write it as a decimal, you should get something like 3.040 ... Right, it's a decimal that goes forever. And then we have for our Y, our vertical component, 3.552, I believe. Okay, so there's our U plus V vector. Okay, so you just add the vertical components and the horizontal components. And we have now our 3.040, which means we're moving to the right. Excuse me. 3.040, and we're moving up 3.552. That would be in quadrant 1 if we were drawing that vector. So if I was to draw a little, I'm going to make it here to the side. If we had a resultant vector, there's U plus V in this case. Right, 3 to the right, 3.5 to up. All right, so now we're going to do, remember this symbol right here, this double absolute value, remember that means magnitude. So that would simply, I'm going to have, I'll write it right here. That would be equal to the square root of, well, we're going to take U plus V, this is the magnitude of U plus V, and we're going to take our 3.040, ... square it. So make sure you go back and recall that value in your calculator. You need to be very organized with the calculator to work on these. And then the same thing for the vertical component form. And that's how we can find our magnitude. Just take your x component, square it, y component, square it, find the sum. Then of course take the square root. You should get something like 4.675. So this would represent our magnitude of our resultant vector, which is U plus V in this case. Okay, so the last thing we want to determine is the directional angle. Okay, so let me slide this down a little bit. So with all that taken care of, I'm going to erase this so it's a little bit easier for us to work. Okay, so we're going to come over here. This part right here, we'll kind of just borrow some space over here for a second and section it off. All right, so we're trying to find theta. So you have to be careful. Remember, this is tangent. Okay, and we're trying to find the directional angle of our theta. Now remember, it's in quadrant 1 that we drew our u plus v. So we don't have to worry about subtracting from 180 or adding 180 or subtracting from 360. It's just whatever the angle is. It's in quadrant 1. So in this case, it's tangent of theta equals, well, we have our component form right there above it. We have the 3.040 and 3.552. Okay, so remember it's always the b over the a. So our vertical movement, 3.552 dot 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 divided by 3.040 dot dot dot. And make sure you're going back up, selecting those values in your calculator. We're not going to do any rounding to the very end, just like we did with everything else thus far in the class. So you should get something like, in degrees, 49.441 degrees. Okay, so let me go highlight the important pieces because there's a lot going on up here. We have our resultant vector here when we added u plus v. We have our magnitude, and we have our directional angle. And remember, since it's in quadrant 1, we don't have to worry about any type of other math associated with it, like adding 180, subtracting 180, that kind of stuff. All right. Now, how are we going to use this? So, example 8 is going to give us that opportunity. So, a plane flying with a bearing of north 65 degrees east. Okay. So if we were going north 65 degrees east, that would look something like this, which means we have 25 degrees left over. Okay, so just to kind of keep this clean, I'm going to draw our vector for our plane. Remember, this is 25 degrees. Okay, and it says it's going 500 miles per hour at that time. Okay, that would be our magnitude. Okay, and since this is going back to, let me write this equation from earlier, g equals a plus w. The vector we just now wrote is actually vector a. Okay, so I'm going to label that. This would be like vector a. Now, a tailwind that adds to the plane's velocity is blowing in the direction north 35 degrees east at 80 miles per hour. Okay, so let me do a little bit of bearing for a second. If I remember the north, south, east, and west lines, or little x and y axis, if we went north 35 degrees east, that would be that direction, north 35 degrees east. Okay, so if I drew that vector in, 35 would be in this position, which means 55 would be in that spot. All right, so just to kind of keep it a little bit cleaner, we know our vector is heading in that direction. Okay, that's our wind. And we know that this angle right in here, I'll go ahead and write it real quick, is 35 degrees. Squeeze it in. There we go. That's 35 degrees. And this one on the outside is 55 degrees. Just get as much information as we can. And this is vector W. Okay, that represents vector W. All right, and what's going to happen, our resultant vector is the one we're connecting from the beginning here at the origin all the way to the end. That's our resultant vector, which in this case is our ground speed, which is the actual speed, the actual path that the plane will take after wind has been applied. Okay, so that's like a picture of our situation. Let's see if we can get everything drawn now. So first thing, okay, everything calculated rather. So we're looking at this. It says express the actual velocity of the plane and determine the actual speed and direction of the plane. So here's our air. So our airspeed represents our plane, what direction it's pointing, what direction is how fast it's going. Well, it told us the speed of the plane was 500 miles per hour. That's the direction it's going, and how fast it's going, and the direction it said was north 65 east. Well, remember our directional angle is from the positive x-axis. So that's what we indicated that 25 earlier. So we're going to say 500 cosine of our directional angle, which is 25 degrees, and then 500 sine of our directional angle, 25 degrees. Okay, we're going to do the exact same thing for the wind. So the wind is that vector in red. So our magnitude, well, it tells us that the speed of our wind is 80 miles per hour. So 80 would be our magnitude. And we're going to say cosine of the directional angle of the wind. Well, the 35, remember, that's the bearing. The 55 out here, so you can see I drew this little positive and negative. Here, I'll extend this out. That's like our x and y axis. This is the angle that we're concerned with. Right, the 55 degrees is our directional angle. It's the angle that's created with the positive x-axis. So 80 cosine of 55 degrees, 80 sine of 55 degrees. Now we can go to our calculators and see here's this equation up here at the top. A and W, we plug those in. We're basically just adding them to get the ground vector, our ground speed, which in this case is the velocity of our plane. Okay, so I'm going to write, I'll say velocity, just so you understand that's what we're looking at, of our plane. I'm going to put G as well. I just want you guys to understand those go hand in hand a lot of times. Well, for this problem it does, because it's the speed of our, actual speed of our plane. So if you add those using a calculator, you get 499.040, dot, 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 and we get 276.841. And once again, dot, dot, dot. So it says express the actual velocity as a vector. We have it. That's this part right here. We just solved it. All right, so vector G, our actual velocity, our actual speed, after wind has been applied. Or, I'm sorry, just our actual velocity vector, our actual component form. Now it says determine the actual speed. Well, the speed would be the magnitude of our vector, which I'm saying is G right now. So we're going to go in there, we're going to do the square root of all that stuff that we did earlier, the 499.040, dot, dot, dot. Make sure you go and recall it in your calculator, squared, plus the 276.841. We're going to square that. This is going to help us get our actual speed, which is approximately 570.686. And we're talking about miles per hour. So that's the actual speed of our plane. Okay, so the last piece we need to figure out, just kind of try to keep it all on the same page, up over here, is the directional angle. So we're going to say, hey, tangent of theta is equal to, well, we're going to use our component form of our vector here, the 499.040 and the 276.841. Remember, it's always B over A. Notice I don't care about positives and negatives or anything. They're all positive here, but I don't care about it. I'm just going to use those numbers. So 276, and I'll show you later what I mean by that, 0.841 over 499.040. So you can go inverse tangent, so second tangent in our calculators. This vector is in quadrant 1. You can see a positive and another positive, so we don't have to worry about adding or subtracting anything. So our directional angle is approximately 29.019 degrees. So we have our actual speed, 570.686 miles per hour, and the direction of our plane, 29.019. Okay, so now what I want you to try is example 9. Try that out on your own, and then when you're ready, start the video back up again, and we'll have the key up, and we'll talk about the results associated with that. So once again, just pause the video and see what you can do with example 9. Okay, so here's example 9. We kind of have our diagram over there, just a rough sketch, air, wind, and ground speeds. So the first thing we know is that the speed of the plane is 180 miles per hour. We have a bearing of north 50 degrees west for our air speed. So you can see here's that 50, the north 50 degrees. So that means that if we're trying to find the directional angle, it would be all of our 90 plus 50 more. That's how we got the 140 for the directional angle. Because remember, it's the angle created with the positive, one over here, the positive x-axis. So 90 plus 50 more, that gives us our vector A. And then it says the wind is blowing from west to east. Okay, so remember we're going to add that vector onto our airspeed if I was drawing it. So from west to east, that means it's going directly straight to the right, which means the angle created with the positive x-axis, the wind blowing from west to east, is 0. That's why we have cosine 0 and sine 0. And of course the 40 is our magnitude, it's how fast the wind's blowing. So we have 40 cosine 0, 40 sine 0. And then what we're going to do is we're going to find the vector, our component form of our vector, for the ground speed, the actual path that our airplane would fly if it's trying to go this direction, the 140 degrees, and the wind pushing on it right there. So if we did that and we add those two vectors together, we get our ground speed, which is airspeed plus wind. That's the negative 97.887 and the 115.701. So this is our resultant vector. It's component form. So now we're going to find the ground speed. That's like the magnitude. Now I wrote the negative in here just so I want you guys to see where it came from. You do not have to worry about negatives anymore once you get past this point. But either way, it doesn't matter because you square a negative, you get a positive. Same thing with the 115. We're going to square it, find the sum, and we find out our plane's going 151.555 miles per hour. So that's our actual speed. And then we're going to go do the directional angle. Now, here's the part you need to be careful on. Notice negative 97.887 and 115.701. That would be in quadrant 2. You can see it's kind of barely in there, but I've drawn vector G here in quadrant 2, which means you have to be careful with the directional angle. All right, so here's what I'm saying. Our final vector, G, ends up over here in quadrant 2. So if I was to draw that down and create a right triangle, we need to find this angle alpha. And once we find that angle alpha, go back to the problem. Once you find that angle alpha, which you can see that's where I was working here, then we can find our directional angle. All right, so we need to figure out this right triangle, its pieces. All right, so using our component form of G, that's why I wrote tangent of alpha is 115.701, and notice, here's the part that's important. I did not include the negative on the 97. Just like I said earlier, once you get past your vector and you get into doing computations, the negatives are no longer needed. We just need to figure out the measure of those angles, and then we can just use our reasoning to figure out what the directional angle is from there. So do not write the negative. Just go ahead and type inverse tangent or second tangent in your calculator of the 115.701 divided by 97.887, which would give us this 49.767. So right here, you can see I draw it. That's the 49.767, where the alpha is at right now. So in order to get our actual directional angle, we need to go from here to here. So we're going to say, hey, 180 minus, I'll put theta, 180 minus that alpha would help us get our actual directional angle. So that's why I subtracted 180 minus the 49.767 in order to get the 130.232. Okay, so if you want to try this one on your own, you're more than welcome to, and then check with me. I'm going to do this last one together just because it's technically like a different application rather than just a plane flying in the air with wind being applied. We have two forces of 10 and 30 pounds respectively acting on the object of in the direction of force 1 is 70 degrees, and the direction of force 2 is 25. So I'm going to say, really, wording's a little bit weird, but the 10 matches up with the 70 of force 1, and our 30 matches up with this force 2 of 25 degree directional angle. Okay, so force 1, our magnitude is 10 times cosine of, what's our angle, 70, and then 10 times sine of 70. Force 2, well, we have a magnitude, that's the 30 pounds is given to us, so 30 times cosine of 25 degrees, and then 30 times sine of 25 degrees. So now we have our force 1 and force 2 component forms of our vectors. So what we want to do is we want to add those together in order to get our resultant vector, our resultant force. Okay, so our resultant vector, remember that's just equal to our force 1 and force 2 vectors add together. All right, so that would be, after using our calculators, 30.609 ... and 22. Let's see real quick. 075. So that's our resultant vector, and from there it says find the magnitude and direction of our resultant force. So we're going to say, all right, our magnitude, right? Remember it's equal to, you take both those pieces, 30.609 ... Make sure I put that, square it, and we're going to add that to the 22.075 and square it. All right, and maybe you're going to get something approximately to 37.739 pounds. Since it's magnitude, we know it's pounds. That was the units given to us at the beginning. So we have, find the magnitude, and we're going to highlight that. Got it. There's our magnitude. So the last piece we need to find is the direction of our force. Right, so we found the magnitude, now it's our direction. Slide this down a little bit. So remember that's going to be using tangent. So now I have tangent of alpha. Notice that we're in 30.609 and 22.075. If I was to draw just a quick sketch of that, which I don't think is a bad idea when you're doing these. So I'm going to use this part to draw a quick sketch. That's 30 to the right and 22 up. So if you want to get a visual, you know it's in quadrant 1, so we don't have to worry about adding from 180, subtracting 180, or from 180, or subtracting from 360. So we're just going to have tangent of theta then, no alpha needed this time, equal to, well, our vertical component, 22.075, over our horizontal component, 30.609. We can use inverse tangent to our thing right there. We're going to find that it's 35.799 degrees, which represents our directional angle. All right, so that's the gist of the applications as far as our notes are concerned, the vectors. Now, I want to make one little side note real quick, is that we were talking about ground, our actual speed, right, equals airspeed plus wind speed. Okay, so we have our vectors. On our examples, I gave you the air and the wind, but then remember, it doesn't have to necessarily be that way. Since it's an equation, if I gave you the actual speed and maybe I gave you the wind, then you can say, hey, here's the path that we need to point the airplane. Here's how fast when you try to get the engines going, you know, and with the wind being a factor. Or, you know, otherwise I could say something like, hey, I gave you the ground, I gave you the actual path that's going, here's the airspeed of the airplane. What's the wind have to be in order for all of that to match up? So you're just doing normal equations. So if I gave you that, for instance, I gave you the ground and the air, in order to get the wind, it's just solving an equation. You would say the ground minus our airspeed. Which means you're going to do the same things you're doing earlier, but now you have a negative because you're going to have to distribute in there or subtract when you're just doing subtraction. It's the same thing. Just want you to be aware that that equation can move around. I'm not going to just always give you the airspeed and the wind speed. It's going to vary a little bit. But what you can now do is finish all of day one's assignment. Make sure I pull it up, get a visual here. So you can finish all of day one. Like I said, all these problems down here at the bottom that might have been a little bit more difficult. So now you're capable of doing those. Really get look at those and make sure we feel good about them. There's a variety of different problems. When you finish that, day two, pull it up so you can see it. Some more vector applications. Save number one on this particular handout for your last problem. Do that one last, actually. And then go through the rest of these and see if you can work those out. It's a lot of ground equals air speed plus wind speed. There's a couple of other ones like forces, but I think you'll be okay. I think I took out one of these. Let me make sure I see which one it is. So here's the key. Don't just work off the key. Make sure you go through it. But number 9, there it is. I omitted number 9. And I didn't put number 13 on there. So you don't have to worry about that one either. So it's 11 problems. So you should now be able to do all of those problems and get a good practice and have a lot of vectors we can go through. And then when we come back together, we can answer questions and we'll go into what's next, kind of the natural step forward from vectors. You guys have a great day.